Heisenberg uncertainty principle can be derived from the theory of operators without great effort. In particular, we will consider two operators, A and B, and both A and B are Hermitian, so A is equal to A dagger, B is equal to B dagger. I will define another operator that I will call delta sub A, which is equal to A minus the average of the operator A. The average of the operator A can be calculated by using a generic state psi, like this, psi A acting on psi. This is a definition if you want. And I can also define delta sub B equal to B minus the average of B. Now it is straightforward to see that the averages of these operators, delta A is equal to 0, and also the average of delta B is equal to 0 from those two definitions above. Whereas if we want to calculate the variance of these two operators, we have to calculate delta sub A squared, because of course the mean is equal to 0, therefore this is equal to the variance, which I can call sigma sub A squared. It is by definition equal to psi acting on delta sub A squared psi, and something similar for sigma B. So we can define sigma B squared as the expectation of delta sub B squared, which is equal to psi delta sub B squared psi. And now I will define another operator that I will call O sub lambda, and I will define it like this. It is delta sub A plus the imaginary unit I times lambda, lambda is a real number, times delta sub B. Now it is quite easy to see that O lambda is not Hermitian, because if we take O lambda dagger, this is equal to delta sub A dagger, but delta sub A dagger is equal to A dagger, which is equal to A, minus the complex conjugate transpose of a constant, which is a constant. So of course delta A dagger is equal to delta A, and then we have to take the complex conjugate of the imaginary unit, which gives me a minus sign, I times lambda, lambda is real, so I will get lambda times delta B dagger, which is delta B. O lambda dagger is not equal to O lambda, therefore O lambda is not Hermitian. Now I want to consider O lambda acting on a generic state psi, and in particular I want to consider the magnitude squared of this state. Therefore I can write it like this. I will put O lambda dagger here and psi written as a bra. Using this notation, this quantity is of course greater than or equal to 0, because you can think of this as a magnitude squared. But now we can also substitute the expression for O lambda and O lambda dagger here. Therefore I can rewrite this as psi, here I have delta A minus I lambda delta B times delta A plus I lambda delta B acting on psi. Now I just have to do a multiplication here. This will give me psi delta A squared, and then I will get a term which is equal to plus lambda squared delta B squared, and then I will get some cross terms that will give me a commutator. In particular, I will get plus I times lambda times delta B times delta A minus delta A times delta B acting on psi. This quantity here is of course equal to the commutator between delta B and delta A, which by definition is equal to B minus average of B, A minus expectation of A. These expectation values commute with the operator, so this will be equal to the commutator of B with A. And now if I write this quantity by using linearity, I will have psi delta A squared psi, which is equal to sigma A squared, and then I have plus lambda squared times sigma B squared, and then I have plus lambda times psi I commutator B A psi, and we have to remember that this quantity is greater than or equal to 0, so this is a real number and it should be non-negative. This is true for every value of lambda. Lambda is a real number, so this is true for every lambda over the real numbers. You can think of this as a parabola. In particular, the parabola is always greater than or equal to 0. This means that the discriminant of the second degree polynomial equation is less than or equal to 0. Therefore, we have that this quantity here squared minus 4 times this quantity multiplied by this quantity should be less than or equal to 0. So we have psi I commutator B A psi squared minus 4 sigma A squared sigma B squared is less than or equal to 0, and from here we get that sigma A times sigma B is greater than or equal to the magnitude of psi I B A commutator psi divided by 2, and this is the most general form that the Heisenberg uncertainty principle can take. Now if A is equal to the position of a particle and B is equal to momentum, that I can write as minus I times h bar gradient, the commutator BA is equal to minus I h bar, and then we have the gradient of the position, which if I write using index notation I can write as di xj minus xj di, and this is equal to minus I h bar Kronecker delta ij plus xj di minus xj di. This will give 0, and therefore we can write that the expectation of the commutator will also be equal to the same quantity, because that's just a number, so this is minus I h bar delta ij. Therefore we can rewrite it like this: the uncertainty in the ith component of position times the uncertainty in the jth component of momentum. You can also call this sigma xi if you want, so this is just a different notation, and you can use sigma pj for the uncertainty in momentum, but that's just a choice. This is greater than or equal to h bar times delta ij divided by 2. This is a frequent formula that you encounter when discussing Heisenberg uncertainty principle.